All right, well, it's 11 o'clock, so let's get going. Welcome, everybody. This is a session on Pangeo in action. I thought it would be interesting to have a session about this because it seems like the Pangeo activity is getting some traction, and just to hear what people are doing with it and any problems they have and so forth. So my name is Jeff de la Bojardière. I'm from the National Center for Atmospheric Research. Our speakers today are going to be Amanda Tan, who's going to give us an overview of Pangeo and some work that they've done at University of Washington. Rich Signell, USGS, on USGS Earth Map. Me on some data we've put on Amazon in the Pangeo framework, and then Carl on using Pangeo as a platform for workshops. So we'll do them in that order. I was reminded that we're supposed to put the top 3 takeaways in this Google Sheet, so maybe at the end we'll think of some of those. Worst case, I'll type something in after. Hoping about 15 minutes for the speakers, maybe a little longer for Amanda as the intro, with some time left over for discussion, question and answer, whatever. So with no further ado, Amanda, I'm going to switch to your briefing, which is this, and it looks like it's being shared out on the screen. So great. To make it small, yeah, okay. And it looks like we have seven attendees online, so that's great. All right, and that should.
All right. Okay, good morning, everybody. My name is Amanda Tan, and I am a data scientist at the University of Washington with the eScience Institute. My involvement with the Pangeo project has mostly been on working with setting Pangeo up on the clouds, AWS specifically. And today I'm going to talk a little bit about the overview of what Pangeo really is. If you've been to the Pangeo website, and I encourage you to do that, pangeo.io, I think some of the language there is a little bit confusing on what Pangeo really is, and hopefully my talk today would kind of explain a little bit more about the Pangeo community and the Pangeo platform. So before we actually delve into the technical aspects or the jargon and associated with Pangeo, really we want to think about what are the drivers of progress in climate science. This is really a cycle. We have things like new observations from satellite data. So for example, we have tons and tons of data coming out of satellite missions. The ISAT-2 satellite mission is actually producing about 1 terabyte of data per day. The NISAR satellite mission that's supposed to be launched, I think next year, is projected to produce at least 10 terabytes of data per day. And also we have data from simulations. So for example, we have data from the CSM lens, which is about 5 terabytes of data. And also a lot of times, all these new observations and simulations are coupled together to produce new ideas. And this is an example of equation from Martin Clark's paper on a unified approach to process-based modeling. So really the question is that scientists are dealing with something that is now known as the data deluge. Yes, sorry. Oh.
Just 1 second. So let me say stop sharing.
This conference will now be recorded.
You want me to present you? Okay. Let's see. Let me double check.
Okay, So we were at the next slide.
Just click on the slides.
Oh, okay, here we go. All right, so it leads us to the current setup that a lot of us are familiar with, especially really old school scientists, is this image of your data sitting in a data center somewhere. This is actually an image of the NASA Pleiades Supercomputing Center, where you see racks and tons of servers that are in a room, and it takes a lot of energy, right, to actually run these data centers. It takes a lot of our time to download data from these data centers, not only in terms of the time that is needed to download this data, search for this data, but also the manpower that is required to actually run these data centers, and then also to run the clusters or the storage facilities that your own storage facilities when you actually download this data from all these data centers. And this image on the right here actually is a computer that we had been using in one of the labs in the university. And you can see that's actually running on Windows 98. You might actually have to look at it more closely. And, it's dismantled because we need to keep putting in more and more hard drives to download the data. And as scientists, we're also very familiar with this notion of data hoarding. If you don't have physical access to the data, if the data is not stored on a computer that you own, you don't feel like it belongs to you at all. So the question is, what kind of science do we want to do with this data that we have? So scientists want to do things like take the mean and calculate the global mean sea level. Or do you want to create, publishable maps? And the image in the middle is actually to analyze the spatial temporal variability and create maps of, for example, marine hotspots. Or they want to look at things. The new thing now is machine learning, right? How do we do deep learning to do climate analytics? So scientists really need to process all this data. And when we talk about the data these days, it's really huge amounts of data, and it's just not feasible for you to download the data and then to run it on computers that sit under your desk. So the Pangeo project really is trying to address this challenge of the data deluge. One of the core fundamental questions that the Pangeo project is trying to address is how can we develop flexible analysis tools that meets the climate community's diverse needs and ability to scale to petabyte-sized data sets. And some of the action items that have been taken to address this challenge is really to foster collaboration around open source scientific Python open source Python ecosystem for ocean, atmospheric, land, and climate science, to support the development of domain-specific geoscience packages, and to improve the scalability of tools to handle petabyte scale datasets on high-performance computing and cloud platforms. So throughout my talk, I would be mentioning open source a lot, and there are reasons for the Pangeo community and the Pangeo platform to use open source. So again, if you go to the Pangeo website and you click on that first page, it tries to explain to you exactly what is Pangeo. And it's a little bit confusing sometimes that people try to say, how can I get one of these Pangeos? And what Pangeo really is a community platform for big data geoscience. It's a cohesive ecosystem made up of an open community where you share your problems, you share your solutions on an open platform like GitHub. It's made up of an ecosystem of open source software, and it is also made up of infrastructure that is open. So when I talk about open, we're really referring to the scientific Python stack for data science, all these open source packages that is built on top of Python. And what this image here really shows is that there are lots of packages that are built on top of the core Python language, and then on top of packages that are built on top of Python, right? So for example, Jupyter, for example, X-ray and dask, and then there are more specific, domain-specific packages like CartoPy and Iris. But Pangeo, as a computing platform, is made up of three fundamental Python packages. It has Jupyter as the web-based interactive interface for you to access computing on the backend and to access the data storage on some of these distributed storage systems. We use Xarray for a lot of the data manipulation. And also we use dask to kind of farm out all these computational processes to multiple processors. So this is really the overview of what the Pangeo computing architecture really looks like. So when you talk about analysis-ready data, we're talking about mostly referring to data that is stored on the cloud, where it's in a globally available data storage. And in the front, you are able to access this data. You're able to access some of the tools, like I mentioned, dask and Xarray, through a web browser on your laptop. And we use Jupyter for that. So when we talk about the Pangeo platform, ideally what you would do is you would go to your web browser and you will type in a URL and it will pop up an interface, a Jupyter Notebook interface or a Jupyter Lab interface. And all these processes like the Xarray Python package or the data be stored either on the HPC system or on the cloud. So let's talk a little bit about some of the technology behind Pangeo. So when we, so I mentioned Xarray, and Xarray is really a Python package that's built on top of NumPy to work on multi-dimensional data sets. So multi-dimensional data sets, for example, are data sets like climate data sets that have they have many variables. Xarray doesn't necessarily work only with data sets that have 3 or 4 dimensions. We can work on data sets with many, many dimensions. So if you have a data set that has temperature and precipitation and pressure and elevation, Xarray is able to manipulate these data sets very easily. And so why do we use Xarray as opposed to just merely using pandas? Is because a lot of climate data and a lot of data sets out there in the real world really have labels. So labels are things like temperature and precipitation, and they're just not made up of just numbers. And so Xarray really offers this very intuitive and concise way to manipulate multidimensional data. And this is really just bullet points of what Xarray does. So label-based indexing and arithmetic, interoperability with core scientific Python packages, out-of-core computation on data sets, and a wide range of input and output options. So you can work with NetCDF data, you can work with HDF, you can work with JOTIS, you can work with ZAR, and you also have multiple very advanced tools to actually manipulate the data. So you can do things like group by, you can slice and dice or resample. And then the other core Python package that really makes up the Pangeo computing platform is something called dask. And dask in its most simplest terms, I think Rich is actually going to demonstrate this really powerful, awesome tool, capabilities of dask, is really dask takes your multi-dimensional arrays that multi-dimensional data set that I talk about that you convert to arrays using Xarray, and it farms out all these processes onto different nodes. So you can actually run dask on your own laptop. If you have, for example, 4 processors on your laptop, dask is able to farm out some of these processes, this data manipulation processes, onto all 4 cores in your computer. So if you take that, the power of dask, being able to farm out processes and put them on the cloud, then you're able to utilize the scalability that comes with cloud. So essentially you have near infinite computing power. And that's why coupling Xarray with dask on the cloud allows researchers to actually really just harness this computing power that's already available, right? And so you don't really have to build more stuff supercomputers. You don't have to put more manpower into buying more servers and use more money to actually get more servers. And then finally, the other core element of the Pangeo computing platform is Jupyter. And I assume that most of us are familiar with Jupyter. We used to use Jupyter notebooks to actually access all these backend tools for Pangeo. And now we've actually upgraded to Jupyter Lab, which gives an even more intuitive way of accessing data and doing visualization and analysis. Then comes the really that question that a lot of people in the room like to ask is, so how do I actually build my own Pangeo? Should I build my own Pangeo? What does it take? You actually can build your own Pangeo. You can build a Pangeo, your own Pangeo computing platform. You can that gives you these tools of X-ray and dask with a Jupyter interface on either ranging from everything from your own computing cluster to an HPC system. You can even do it on your own laptop. But again, if you really, really want to harness that computing power, you would want to build Pangeo on the cloud. So the way that we at the University of Washington, what we have done at the University of Washington is to use to build something to build an easier way to deploy Pangeo through a GitHub repository by using continuous integration. And actually, this is the GitHub repository right here, Pangeo Cloud Federation. And really, all you need to provide are some cloud credentials, and you can use this repository, you can clone this repository and be able to set up your own version of Pangeo in a few steps. Some of the custom Pangeo deployments are, for example, again, a NASA Pleiades. It's also been installed on the Cheyenne supercomputer and NCAR. We have worked with getting Pangeo set up on Google Cloud Platform, Azure, and AWS. And these are some of the custom deployments, so Polar, Solar, Ocean, HydroShare. These were all built using that methodology of continuous deployment through a GitHub repository. There are some notes of caution, which I will address in a couple of slides later. Those are some of the lessons that we've learned in trying to set up our own Pangeo. This next slide actually just shows you the difference between setting up Pangeo on a government HPC versus the commercial cloud. So again, one of the sticking points about installing on an HPC system really is access. A lot of these HPC systems are usually just accessible if you have a federally funded project. So really, what is Pangeo? Pangeo is a scientific Python ecosystem made up of already existing open source tools like Jupyter, dask, X-ray. And it really, what the Pangeo is trying to do is to utilize a lot of software that's out there. There's no sense in reinventing the wheel. And when we talk about open source, the Pangeo project really tries to encourage community input, community around building all these open source tools. So if you need to have a very niche and specific geoscience package, the Pangeo community really encourages you to use fundamental open source Python packages. Some of the problems really that has led to Pangeo being developed are something called fragmentation problems. There feel tangible incentives for researchers really to share their source code. So a lot of funding agencies don't stipulate that, but they are starting to do that now. And also it's easier to work with something that you're already familiar with, or if it's homegrown in your own lab, that's something that's easier for you to work with. And the result is a lot of geoscientific research is really not reproducible. And it doesn't really work when it's ported from one system to another. And there's also something called dark replicas, where again, data sets are replicated over and over again. And so the Pangeo project is really trying to address this problem. So in our work with Pangeo, there are lots of lessons that we have learned. One of which is that Pangeo is really only in development mode. It is not something that is ready to be deployed on an enterprise level or in a large scale level, mostly because up to now, our funding has been in terms of testing the system. So we have run into issues like security with Kubernetes, right? Or security issues of other people being able to log onto your Jupyter systems, or your data just disappearing. And so really just understanding that all these problems exist, and that Pangeo is not, this one solution to solve everything. Then there's also issues of cost management. When you run something in the cloud, there is always this potential of having something called zombies, right? Where you run up some resource on the cloud and you don't know what it is, and it just keeps sucking money. So there's one of those things where you really have to learn about the cloud fundamentals before you can actually deploy your own Pangeo. And then there's also this notion of long-term sustainability. We are constantly going back to the well for more money. And this is really just not sustainable, even though Pangeo is built on a lot of open source software, where ideally it's supposed to be self-sustaining, because if you have a lot of community buy-in to some of these tools, that it will be self-sustaining. But if you're running Pangeo computing platform on the cloud, for example, somebody has to pay for the cloud resources. And if you have a huge community that wants to use this platform, how do you actually sustain this for that community in the long term? Some of the other things that we've been doing is really talking about governance around Pangeo, and also trying to partner with, try to find collaboration with community partners. And so how can you get involved and how can you sustain Pangeo? Pangeo really depends on community buy-in. It really depends on you going out and saying, look, I have benefited a lot from running my analysis on polar.pangeo.io. I would like, for example, some kind of federated or some kind of federated, Pangeo platform, or I would like to actually run it myself. And you go out and talk to funding agencies about sustaining this in the long term. And also really the other thing that really sustains Pangeo and to be involved in Pangeo is really to work on contributing to the underlying open source software stack that Pangeo is built upon. So building more tools that would run on Pangeo and building more tools that demonstrate how Pangeo can help you in your own research. So with that, I think I think I am done. So, thank you.
Okay, we have a few minutes for questions, and I think, Amanda, you said you need to leave.
Yes.
To another
Yeah.
talk. So,
Yeah.
so are there any questions for Amanda?
I guess this is a community question, but I was just interested if you think that Pangeo will be interested in integrating it all with this NSF initiative, the URSSI thing that we heard about during the plenary. I know it's a pretty new project, but it sounds like they're interested in doing software workshops as well.
Yeah. So I think the Pangeo governance community is really just open to any kind of collaboration. There is really, I think with government agencies, there's more of a, like, we're okay. I think they're okay with, just like collaboration. There's also been talks about really working with industry partners in terms of running this as a service. So yeah, I don't know if that helps answer.
Are there any other activities besides ESIP that Pangeo is doing in terms of building that open source community around it so that it can sustain itself? Like, I know you're active in ESIP, but after your funding is over? Is there some sort of model to keep it alive?
Yes. So the question is there some other funding organizations beyond ESIP for sustainability? And we have grants from NASA and NSF in terms of really building more of this technology, the Pangeo technology. So for example, we have funding from NASA and actually building something called dask gateway, which is really another level of that showcases the awesomeness of dask, where you get to not only kick some of your computing processes to the cloud, but to different clouds in different regions. And really, I think they're also working on being able to kick some of the processes not only within the same cloud, but different clouds. So those are some of the examples of us trying to make Pangeo more sustainable. We're trying to think beyond vendor lock-in. We're trying to think beyond just one funding agency. If somebody has funding from other agencies or somebody that has funding from cloud providers, how are they able to integrate that with the Pangeo stack? And also a lot of the people that are involved in the Pangeo community are really, really strong, not proponents, but strong. They've been really heavily involved in a lot of open source tools. So for example, one of the really fundamental people on this project is Joe Hammond. He's a really core member of Xarray, and he's continuously thinking about how can he improve Xarray so that when Pangeo actually does use Xarray, that it really is a long-term technological sustainability thing. Yes. Thank you.
Okay, let's thank our speaker once again. Thank you very much. Okay, and Rich, yep, I think you're up next, so let's close that. And I want to not close the wrong thing. Oh, wait, you're not using PowerPoint. You're using the browser. Yep.
Second browser tab there.
Okay. That one right there. That second one. Second from the left. Okay,
Yeah.
you go.
Should I start in the middle of my presentation?
It's not sharing the screen.
Oh, it's not sharing again. Okay. So you need to share that. Did you share the whole screen? Because I'm going to go to another.
Yeah, share the whole screen right now.
Okay. All right, so that was a nice introduction to Pangeo. And what I'm going to do is spend most of my time doing a live demo, which is because it's always exciting. And it's especially exciting because I found out that our notebooks are running on spot instances, so it could just crash in the middle. But it's never crashed yet, they said. So I figure this challenge. I know, right? Well, I guess when it's going to, no, okay, we're going to be good. So I'm going to talk about the USGS Earth Map Pangeo. So I'm a research oceanographer at the USGS in Woods Hole. I put a bunch of folks on here because there's a bunch of other people who are poking at this Pangeo thing within the USGS doing cool, like water, like stream gauge, river network, satellite imagery, ecosystem stuff. I'm not going to talk about their stuff today because I don't have time. I'm just going to show you one demo. But we've had help setting this up, as you just heard from Amanda. It can be a little challenging to get these things up and running. There's some folks from our cloud hosted solutions team there. And we've actually had a lot of help from Amanda and the folks on the NASA Access project and getting this stuff going on AWS. So what is Earth Map? You actually heard, if you were in the plenary, you heard Sky Bristol mention this. This is something that the USGS director, Jim Riley, is very excited about. And it's this sort of situational awareness, as you sort of heard, like the holy grail, right? All the sensors are feeding into this like coupled modeling system, sim Earth kind of thing, and delivering the data, of course, to smart sensors, and then the sort of Internet of Things kind of. So if you're an emergency response person, or if you're a manager or whatever, you have your, you can get this stuff is on your fingertips. And if you think this is too future world, then you can check out the Alexa skill called Storm Sense, where this was done with a bunch of sensors and models in Chesapeake Bay region. So this is a little cartoon of showing how this might work. You have your sensor domains, the sensors feeding into the cloud, and the analysis is, and the processing is happening there. The models hopefully are actually running in the cloud also. All their data, of course, is in the cloud. Over here, we have our Pangeo environment to do our sort of research computing on this, and perhaps also drive applications. And that would connect up with NASA Earth Map, Pangeo, and the NOAA. Different agencies would be running their different Pangeo instances. Maybe we'd be sharing the same kind of infrastructure in terms of what kind of packages we're using and approaches, right? So really kind of maybe in some sense the ultimate data center consolidation. So I just want to show this slide that Amanda showed again and highlight a few different things. One is that, as she pointed out, we have our data here sitting in these in the cloud object storage. I just want to emphasize there's no data services between the cloud storage and dask. Okay, so except for S3, and so I've been a proponent of web services for 20 years, and it feels kind of weird to not be using web services here. But we're actually going right to the data and extracting just the data we need from cloud storage. That's a real fundamental thing. And while we had X-ray here as a core package for dealing with model output and remote sensing data, you can totally use this same thing with pandas and and with large tabular data. And we've got several workflows that show doing that. And so instead of using ZAR or cloud optimized geotip over here or HDF, you might be using something like Parquet. And another key thing that we often leave off of this slide is the visualization part. So to actually be a scientific platform, you need to be able to interact with your data visually, and you need to be able to do things like scribble on an image, like for doing like classification and things like that, and have the results come back to Python so you can keep on working. That's a really key part. And plus, I like my little slide, picture on the right of the user just sitting in the park with their Chromebook or and their Wi-Fi, their hotspot, and doing all this crunching on terabytes of data. You can work from anywhere doing this approach. I do it all the time. The biggest problem sitting in the park is the screen glare. So I'm at the USGS. I actually supervise a modeling group there, and we have, we're going to try to trumpet this more, but we have the only coupled ocean, atmosphere, wave, and sediment transport modeling system. These are all using community models, but they've all been linked with two-way coupling. So in a sense, it represents in a microcosm this Earth map concept, because we have all these coupled models and we have data feeding in. And so we don't have petabytes of data in our group, but we have hundreds of terabytes. So, but we're very selfishly interested in this Pangeo issue. We're not doing climate science, but we have a lot of data and we have coupled models. And so I want to show you an example of something that really came out of our group. We've been running this forecast model for the East Coast in this coupled mode, waves in circulation. We actually we don't run the atmosphere, we get that from NOAA, but we've been running this for 8 years, and one of the guys in our group said, I want to look at the average wave heights over this 8-year period and see if we can see some kind of interaction between the circulation and the waves, because that's what we've got that's kind of new here. And he said, and then he came down the hall a while later and he said, I've been running this thing for a week, and it's halfway through. Like you were talking about that Pangeo thing, would that be useful here? And I was like, yeah, come on, let's do this. So we converted the data to ZAR and we put it on the cloud. And so I'm going to show you a live demo of how that looks working with this data, I hope. All right, so I just logged in. We're going to make that a little bigger, right? Is it Command plus? Yeah, okay. Can you see that in the back?
It is really big now.
Sweet. Okay, so I've got this notebook here. We're going to actually, you know what? I'm going to shut this down. I'm going to, just to make sure. I don't want to start from a running something. And now I have to scroll way down here. And ooh, yikes. Close and halt. Okay, and I'm going to leave this site. Start over. Okay, so now it's not running. It's not green anymore. I'll click on this again. If I can double click. Ugh, I got 3 of them or something. Okay. All right. So we got this. Okay. Wait, now I have to go and restart and clear the output. Okay. So now we're really starting fresh. So what are we going to do here? So we import a few packages. We import Xarray, and we import that HV plot package, which is going to do the visualization, FS-spec, which is going to allow us to open up S3 just like it was a file system. And so here, I actually open up the data set with a Xarray OpenZAR, and you might notice that I'm doing a requester pays. So we're opening up data from a requester pays bucket. As long as I'm in the same region, I'm not going to be paying any egress. And so that's the case here, but it does mean that I have to have credentials to do this on AWS. But now, if we look at the data set, it just looks like regular, could be NetCDF, HDF, whatever data set that I loaded. And it loads quickly because I've just loaded the metadata. Actually, maybe make this a little smaller because it looks kind of ugly. I don't know if you can see that, but so here's our variables and the different sizes. So go down here and let's take a look at a particular variable. Okay, so this is this wave height variable that we want to look at, and we can see that it has a chunks. Okay, so it's 67,000 time steps, 8 years, 300 by 900 or so, and the data's been chunked. This was my decision on how to chunk this in 654 in the time dimension, and then 250 by 250 in X and Y. Why did I do that? Because I wanted to pick a chunk size, first of all, that was around 100 megabytes. You don't want the chunks to be so small that you have millions and millions of things you have to do, but you also don't want them to be so big that you have to read the entire data set just to plot a time series. So 100 megabytes is sort of the rule of thumb we've been using. And now I'm going to fire up this cluster to do the work faster. I hope this works here. And okay, so I said I want to do my work 60 times faster, right? So here come these workers. This is Kubernetes. Spinning up these workers for dask. So on the cloud, we use Kubernetes to have our dask cluster. On HPC, we submit jobs to the queue. On the local machine, it's just whatever CPUs you got. So the only difference is how you start your cluster. Everything else is the same. So here, we're going to keep going. We have a client, and now we're going to say, hey, I want to plot a time series from this wave height variable at a particular IJ location. And here's this cool thing. You just say .hv plot on the end. And instead of just getting if you just said .plot, you'd get a static plot, just a ping. But here you say HV plot, and this is this holoviz package, and you get this dynamic time series. So here's all the data at a particular location, right? Here's all the waves from this forecast model. And now I've got this little tool over here. I can actually, let's say if we want to go look at some time period here, this is gonna, okay, so I can zoom in, right? I can keep doing that. I can do it. Okay, so now I've zoomed in on 2012. Take that off. Oops. Let's see here, go back. Let me try that again. I'm terrible on a Mac, man. Hold down the command. Shit. Okay, never mind. So I'm hovering over Hurricane Sandy here. And this is showing me this really high wave height here on October 29th, okay? So we can go down here, and now I can say, okay, so that, okay, by the way, that took about 12 seconds, okay, to do that plot, okay? So this is a function of how I chose my chunks, right? I can extract a time series and get back within about 12 seconds. And if I go now and do the other thing, I'm gonna take actually just a time slice here. So I'm taking it, so, Xarray has this nice feature where you can just put in a real time and you get back the slice at that time. And I'm going to say .hv plot, and now I'm going to do a map. And I have some things on here like tiles equals true, so it's going to put a tile service on the back. And so you'll see here, just with this very simple command with a few parameters, you get back now a really nice representation of your map at a particular time. And again, I'm going to be able to do this. Come on, Rich. There we go. Okay. So if I drill in here, you're going to see this refresh. Actually, and it re-rendered, this is a really cool thing, it'll re-render that data at the screen resolution, and so all you're delivering back to the screen is those pixels, and you keep drilling in and you keep getting more resolution. And do it again. And now you'll see the model update. Of course, this is not a super, I hope you saw that. It's not a super, fine resolution model. But now I'm going to do the big calculation, okay? I'm going to calculate the waves over the time dimension And I'm gonna let that fly. And so it starts calculating, and actually I should go up and open up the dask dashboard, which shows you what's actually happening with all these workers. So here they are. And so actually, I just changed the view to, okay. So if you hover over here, you can see what they're actually doing. So this is like loading ZAR. So each one of these little chunks, so this is a processor loading a chunk of data, taking the mean and adding it all together, and then everything's happening in parallel. So even though it takes 3 seconds to load one of these chunks, you can do the whole thing, with all these processors, and get back to, and get your result back in just, in this case, 30 seconds. So where this guy was working for a week to do this, you can imagine he was pretty jazzed to see the result in 30 seconds. And the cool thing here is that when we did see the result, we actually saw, if you can see it here, that the waves generally are increasing offshore, but here in the region of the Gulf Stream, there's actually a local maximum at the Gulf Stream. And we haven't seen this before. It's because of the interaction between the currents and the waves. So that's the kind of cool result. That's the kind of thing that, obviously, if you have a toolkit like this, you can do really quickly and explore these kind of things instead of waiting for 2 weeks and, finding out you might have some issue. Okay, so just to finish up, oops. Oh yeah, so some of the challenges, Amanda mentioned some of these, but one of the things that institutions are, some of the problems that institutions like USGS are facing are that we already have HPC that we've paid for, and we're making free to our scientists. So it's not much of an incentive program to say, hey guys, why don't you go work on the cloud? And by the way, you have to use all your project costs to pay for it. So this Earth map thing has been really good for us. It's provided some money from the director down to say, hey, make this thing happen. Here's some money to go explore the cloud, figure out what the real costs are, how this works with your workflows. And it's given us a chance to really figure out, how much does this stuff cost? What are the issues? And some of the issues, are about learning new things. Actually, I should look at my slide here. Yeah, so actually most of the money in Pangeo is spent on cloud storage. There's things like wasabi.com coming along and charge 1/5 of the the storage and have no egress, and is that going to cause Amazon to do respond in some way, or there's all sorts of interesting issues out there. But back to the cloud skills, yeah, there are some things we have to learn as scientists. Certainly having making computing as cheap as HPC is a good idea, but also webinars, these like hackathons, these that the University of Washington has, like Ocean Hack Week and stuff like that, are really, really super useful. But also just communities like Pangeo and ESIP are I think are really where we're going to spread this information out to the institutions, teach the teachers, and really get the word out on this. Cloud optimized data, we've been using ZAR, but it's really it's not clear that we can't read things just as efficiently with HDF. We just maybe haven't figured out how to do that yet in the same context. So we actually have a little project going on right now with the HDF group to use, to actually use the ZAR library, and at the very end, instead of pulling those chunks from ZAR, we're going to pull them in parallel using dask from HDF and see what we get. And then finally, as Amanda mentioned, it has been a struggle actually keeping these things going with Kubernetes clusters and everything, and the changing landscape. And a lot of time has been spent by their group just trying to learn about all this cloud sort of DevOps stuff. And there, hopefully, it'll get better, but also there's companies popping up like SaturnCloud.io, which will actually, if you've got an institution that wants to run Jupyter Hub with dask, which is basically what Pangeo is, they'll do it for you for a surcharge. And maybe things like AWS SageMaker. If SageMaker could run dask, we would have Pangeo already basically provided for us by Amazon. So, and if custom environments were straightforward. So finally, just as Amanda said, come join us, learn about Pangeo on Pangeo.io, follow us on Medium, discuss it on Discourse, chat on Gitter, and we're gonna re-kick the ESIP Cloud Computing Cluster. And so please come and join us there too. So thank you.
How long did it take you to develop that the Jupyter notebook?
So that notebook, one of the great things about this is it's, as Amanda mentioned, is it's actually not doing it's not using anything different than, what I would do if I was doing it on my notebook. I just have a bigger cluster to do it, except for the part of converting the data to ZAR, which I didn't show you the notebook because I didn't have time, but Xarray allows you to read lots of netcdf files, and it also lets you write to ZAR. So that's the pathway that we take there, although there are some issues sometimes with that. And I think Jeff might mention something about the ZAR creation process. Maybe he won't talk about the issues. No issues for you guys, but yeah, anyway, but come see me if, or, bring up an issue if you're interested in this workflow.
Any other questions for Rich? All right, thanks. I think it's maybe because he made the size of his window big, right?
No, it's defaulting to the aspect ratio of the screen as opposed to the projector. So the projector is trimming off the edges. So if we go to the system. We had to do this yesterday. There we go. So now things should line up when they get played.
Okay.
We can identify the appropriate windows.
We could just kind of get to the right there.
Move that over there again. Okay.
I guess to be fair, I should make sure I set the timer so I don't go over. All right. This. Great. Okay, thanks. So my name is Jeff de la Bourgeardière, and thank you for coming to this session, by the way. Before I start with my talk, Amanda had said Pangeo is a community. It's not really a thing necessarily that you download. And I guess the way I think of it is that Pangeo is a community that helps you choose among the huge ecosystem of Python, especially tools to do stuff with data. So there's a lot of stuff out there. Some of it's good, some of it's bad. And on some level, Pangeo has kind of selected some stuff and is helping it along. And I see Rich nodding. Yeah, so it's been very good. I think I'm still a newbie at it, still learning what we can do with it, but I think we've had some good experiences so far. So I'm going to tell you about this data we just recently put on Amazon, and I don't like the view that's showing me here, but whatever. Okay, I apologize. The first two slides I showed yesterday in another session, but there are some subtle differences. So if you were in that talk, you can amuse yourself by trying to find the subtle differences. So CESM Lens, this is the community Earth system model, large ensemble. It's described in a publication by Jen K et al. With the link up there. And basically it's a simulation of climate through the year 2100. So it uses whatever historical data we have, and then it forecasts things. In the forecast, it's assuming what's known as the RCP 8.5 scenario of greenhouse gas concentration. That's the worst case scenario in the fifth report by the Intergovernmental Panel on Climate Change. And it's a pretty complicated data set. There's different grids used for land versus ocean. There's surface data, there's 3D data in the atmosphere, there's 3D data in the ocean, different vertical levels for all that, different temporal resolutions, multiple time axes. So, besides the key period of essentially 1900 to 2100, there's some stuff that goes to 1850, and then there's stuff that goes to the year 0 or the year 400. So there's just kind of weird ends, and a few of the runs sort of stopped earlier than some of the others. And then the key thing, what makes it the large ensemble, is basically the model was run 40 times with slightly different initial conditions, so you can kind of get a spread of what's happening, get slightly different results, and then take an average as a better prediction of the likely reality. Traditionally, the data set were difficult to access and use. They were publicly available from NCAR. It was about 500 terabytes with 150,000 net CDF files. You could download it. You could theoretically download it all if you had room for it. Or if you have an account on a supercomputer, you could compute on it, but you might have to ask for the 2/3 that wasn't on tape, that was on tape, to get moved to disk before you could compute. So now we've moved, not the whole thing, but a subset to Amazon. And I really want to thank the Amazon Sustainability Data Initiative and the AWS Public Dataset Program for basically the free storage and egress we have for this data. And then these people, Anderson, Brian, Joe, Chiffon et al., as collaborators to do a lot of the actual work of converting to ZAR, uploading to the cloud, writing the notebook, that kind of stuff. They were the primary people doing the work. We've given this data set a separate DOI from the original one because it's a smaller subset and it's in a different format. That's it there. It got made public on the AWS registry in October 2019, so just a few months ago. And since then, we've done a little bit of tweaking and fixing of the Jupyter notebook. So we've got about 70 terabytes on S3 with theoretically 30 terabytes left in our allocation that we could add more data to if there's more fields we want to put in. The key use for this data are both global average predictions based on the somewhat low resolution, roughly 1 degree model, but then especially using the low res data as boundary conditions to run new models at a higher resolution. Okay, so now this is a new slide, so if you were in my session yesterday, you can pay attention again. Jupyter Notebook, so we established, oh wait, I just do want to say one thing. So the key thing is we've got data on S3, we put it in ZAR, we have an intake ESM catalog that is an inventory of all the data, and then a Jupyter Notebook that lets you get to it. So I'm going to tell you about each of these things. So the notebook, you can get to it at that URL up there. And what this notebook does is actually try to reproduce 2 figures from the original paper by Kay et al. So this was a brilliant idea by Joe Hammond. So it's sort of doing reproducible science, right? Where there's a paper from a few years ago, here's a completely different copy of the data using completely different software, reproducing those figures. And at the same time, it shows people how you access and use the data. So you could do now new figures by modifying the notebook to your heart's content. Over time, we've tried to make the notebook helpful to new users. In fact, much of the work I did was trying to do that because I was kind of new to notebooks. It's like, wait, what is this? What's happening here? What does it mean when it says % time at the beginning of a cell? Or what is this library? Yeah, no, it's great. But so as I learned some of this stuff, I sort of added more comments and tried to make it a little bit more clear, not only to me as the sort of pointy-haired boss, but to potential other people who are scientists who are used to their own workflows, right? They don't necessarily do this. They have MATLAB on each PC, or they compute on data on their own computer, right? They're not used to using Jupyter Notebooks, they're not used to using the cloud, so we're trying to make it a little bit more accessible to people. So step by step, a lot of comments, and also have started a second kind of more general notebook that doesn't specifically try to reproduce these figures, but would let you say, okay, browse what's the available data, let me choose which one to plot, press go, you plot. Right. So Jupyter Notebook has been good. As I said, it did reproduce these 2 figures. We didn't actually take the notebook one, which is on the bottom, all the way back to the very beginning of the control run. But the rest of it, you can see that reproduction is good. I do want to highlight one thing, though. It's great to do all this techie stuff, but the real problem is that all of this stuff is predicting basically a 5 degree C temperature rise in the year 2100. Okay, so that's the real issue. The reason data matters is because we've got these potential looming problems, and so we need to be able to work with the data, do new simulations, better ones, downscaling, that kind of stuff. Okay, the other figure we reproduced is this one, which is a panel of a whole bunch of globes. Each globe is a different ensemble member. There's some control observations for a specific year, so this is from the paper, and then our version over there. I mean, of course, they look a little bit different. It's a completely different plotting package, but the content of what's on the thing is pretty similar, or should be exactly the same. Okay, then we built a intake ESM catalog. So that's a data inventory utility. It relies on packages on intake as also a kind of catalog and inventory utility, and then Pandas and Xarray, but it's specialized for earth science model outputs. So you could read about it at that URL up there. Anderson Banihiri from NCAR with NSF Pangeo funding is the main developer on this. and it's, new, version 0 point something. What's nice is it really abstracts out the file format and the storage location. So it can say things like, oh, I have data for these variables at these time frequencies, for the historical runs or for the future scenario runs. And somebody puts together this listing essentially telling you exactly where each one of those is, but then the users don't have to worry about where they are. They just say, hey, this is the kind of data I want, please get it for me. So you can browse and filter, basically filter through the data based on the available attributes, and it will return a list, basically a dictionary of the corresponding data objects, which you can just feed to Xarray. In fact, I think this next couple of things are sort of screenshots from sections of our Jupyter notebook. And I'm showing this because I think most people aren't using intake ESM. A lot of people are using stat catalogs or other things, but this is what we've been using, and it's been pretty good so far. So there's basically a URL of a collection file, and in here it describes the overall collection, and then in that file it'll tell you, hey, what's the essentially CSV listing of all of the ZAR stores that we have. And if you inspect that, it tells you, oh, okay, I found this ZAR store, and it's got 5 components, 5 temporal frequencies, 6 experiment, 46 variables, leading to 278 paths, each one of which is one ZAR store. And then you can do things like, hey, show me what's in that. And so this is just the first 10 lines of it. And it's telling you I've got, atmosphere component, daily frequency, the 20th century experiment, these variables, and this is where they are on S3. And then you can say, well, okay, I want to do figure 2 of the paper from K et al. So what I actually need is both daily and monthly data for the atmosphere component and this specific variable. And it returns what is the subset of that. And then you can, of the entire list, gives you just these 5 results. And then you can just feed that directly to Xarray and read the data you want. So that's been great. And then, as I mentioned, the data are stored in ZAR. That's been described before, or mentioned here before. That's the URL for the documentation. Cloud optimized format. So basically it breaks large multi-dimensional data sets into smaller chunks. We did, Rich, choose a chunk size of about 100 megabytes as well. Each chunk is just pure binary data, which can be compressed losslessly, and the metadata is in a separate file, so you can read the data without having to get past the header. The chunking scheme is tunable, so we made a choice. We are, and I'll tell you about our choice in a minute, but I think we'll do some testing on could we have made a better choice and should we redo it. I found it interesting that this was developed for genomics data, the ZAR format, and not for earth science data, and yet it's getting a lot of traction in the earth science modeling community. So here's an example for one variable, one ZAR store for the temperature at reference height variable in the RCP 8.5 future scenario. So it's daily data from 2006 to 2100. It's basically a 4D hypercube. It has 40 ensemble members, 34,000 something time steps. Sorry, should have a line break right there. 288 longitudes, 192 latitudes. Works out to about 300 gigabytes uncompressed data. So at NCAR on our high performance POSIX file system, it's 73 net CDF files. On Amazon, it's just one ZAR store in these 100 megabyte chunks. And the scheme we chose was each chunk has 2 ensemble members, 1 year of data, and the whole globe. We don't know if this is the best chunking scheme. In fact, I think we should maybe break the globe up and change the other chunking variables accordingly. But we want to do some experiments, just some timing and see what's faster, better, cheaper, whatever. Then each ZAR store also has all the ancillary data like coordinates, cell areas, which vary depending on latitude, that kind of thing. So that's how we broke up that one variable. The other ones are similar. So what's next? First, actual use of this data set. So right now it's been a little bit experimental. It's been available only for a couple of months. We'd like to do some new science on it that hadn't been done before, just because now it's more readily accessible. There's at least one private company that does regional downscaling as their business, and already actually had a tiny bit of the lens data on Amazon at their expense. Now they'd like to do some computing on our more full data set and do more downscaling. We're looking into lossy compression. So these are 64-bit floating point numbers, but really we don't have temperature precise out to 64 bits. So how much can you sort of trim off for different variables and save storage space while essentially having an indistinguishably different data set? And then performance tests on ZAR, is it good? Maybe looking into comparing with our original NetCDF. Maybe some improved analysis tools. I think another Jupyter Notebook is in line, and also non-Jupyter Notebook. I mean, I like Jupyter Notebooks, but I think I'd like to see some other stuff out there maybe. And then also we want to put additional climate model data sets up. The CMEP6, the NA Cordex, or the GLENS data, for example, are ones that are candidates for us. And I'd like to see some improved standardization, like use of CF standard names and so forth, which kind of brings me to my concern. So, I was kind of surprised and horrified to see how much heterogeneity there actually is in model outputs, because here we are, working on models together and then running them, and we in theory could have chosen to have, perfect uniformity and CF standard names and the same, maybe not the same grid, but at least some agreement on things. Or everybody kind of does their own thing, and you end up with a lot of heterogeneous model output, and I think that's unfortunate. So now we have to sort of patch that over. And then a global concern, I mean, I think the ZAR, dask, or X-ray Jupyter approach is great, but it really seems to me, at least, still a focus on individual data sets. It'd be great to have a kind of higher level multi-collection view. I'd love to see improved interoperability. I think there's still a lot of data set specific code you have to write. I think Jupyter Notebooks are useful, but not sufficient. If I kind of re-show this little cartoon I had before, but simplified, it's like each data set is still sort of a stovepipe. I mean, it's great, it might work fast, but the next data set is just another stack of storage and ZAR and catalog and notebook. So I'd love it if we could have something more generic where, notebooks are part of it, but we've got this underlying infrastructure of stuff that's usable by all sorts of tools like, GIS software, predefined visualizations of key types, if that's what you really want, that sort of thing. And then a lot of agnosticness about the where the data are located. Okay, so that's my last slide. Any questions?
So if you chunked with the whole globe, does that mean if you extract a time series, you have to read the entire data set?
Yes, you have to read the whole globe to extract a time series. That's why I think we should re-chunk the other way. Now it's very coarse data, right? It's only 288 by 192 pixels. So, that's why that choice was made. I still think,
Maybe not a common use case then, right?
It's not that, right. It's not like you can drill down on, Boulder, Colorado and get some nice detailed value, but kind of on principle, I'd love to see, a somewhat finer chunking in the, yeah.
I guess I have two questions. It looks like Amazon is paying to host your data. Are they paying to compute on this data as well?
No. So we have a 2-year agreement as part of the public datasets program for the hosting, storage, and egress, which is great. But then the computing we do separately. So we have some cloud credits that we use to run a binder hub with Jupyter Notebooks. And we're actually figuring out internally, okay, wait, what do we want to do as actual computing, and what additional data do we want to put that maybe we can't put up for free, right? We already spent a lot of money on our own data analysis and visualization machine, which is not at end of life yet, but someday will need to be replaced. And I think a big question to figure out is, do we buy another one? Or do we instead do as much of the data analysis part in the cloud? I don't think we can do the actual climate modeling in the cloud yet. We need a true supercomputer, but for the data analysis, a lot of that could easily be done in the cloud.
So have you considered a hybrid approach when your data stays in AWS, but maybe you run Pangeo on your local machine or like in the car cluster?
We are thinking about hybrid approaches, including things like dedicated connection that would let us move temporary copies of data to the cloud for computing, and then you just kind of delete it when your result is done. In terms of running locally this is something I'd like to see. One issue I actually have with the whole Jupyter thing is the development environment still, it's a little funky. Like, I'm used to the idea of you write code, it's on your machine, and then you run your script, and I'm talking like IDL, so that shows you kind of how old I am. But when I start the notebook and it's running on the cloud, it's a sort of ephemeral copy. I have to go through some gymnastics to get my modified notebook on my machine and then back again available to run in the cloud. So I like the dask gateway thing that Amanda mentioned, because I think it'd be great to be able to have the notebook user interface running on my laptop, but invoking computing resources either on the HPC or in the cloud.
Since you mentioned IDL, do you find it easy to work with Pangeo? Because IDL abstracts a lot of the separations for you already. It's really easy to do what you want because it's already implemented for you.
Mm-hmm.
Do you have to re-implement all of that stuff in Pangeo from scratch pretty much?
Yes and no. So I haven't actually written IDL in 10 years, right, as I moved into more non-programming stuff. So looking again at code is new. So personally, I find it interesting to try this new stuff. I don't find it easy because it's new, but probably looking at my old IDL code, I would not remember how to do it anyway either. So, but I think a better use case is somebody who actually is and has been a practicing scientist and is used to MATLAB or IDL or just running stuff locally. For them, the leap to the cloud is definitely a difficult one. So we need training and resources for that.
So Jeff, one side question, since you mentioned notebooks. I found the notebooks great, but one thing is that the like things like Git, like source version control software, and notebooks really don't play well because notebook format is JSON. And so when I make some changes in a notebook and then I look through diffs between the previous version, it's kind of very complicated to see what has really changed. So in a way, they're really great, but when you come to sharing code and working in code development, they kind of are still, I wish that things like GitHub or something have a much more natural way to present changes in a notebook, in a much more programmer, sort of like a standard, standard programming language source code file.
Yeah.
So that's something that I find. So I play with notebooks, but when it really becomes serious, I tend to take the code out into a, say, Python file and then proceed there, or make a module out of something and then work for there. So notebooks are great, but kind of not really for serious code development kind of thing. They're just more like common. Did you find the same limitation when you played with it, or?
So I have found limitations, but I suspect that the majority of the limitations may be just my own newness to them, and that Jupyter Notebook expert can just churn through all that. But it does seem like there's a few fundamental things that are a little bit funky, especially when we have our notebook, on GitHub, and then just getting that whole, making changes, making sure they're put in the right place, not accidentally doing something wrong, making it so that whoever runs a notebook now gets a new environment and not everything. It seems a little clunky still, but yeah. Move on. Yes. Before we criticize Jupyter Notebook.
No.
Yep.
Give Carl some time.
Right. Okay. Thanks. Whoops, what did I shut down here? No, we're still, I think we're good. So we're going to close this. So our next speaker, Carl Benedict, last speaker. And
You didn't need to see anyway.
No.
okay, so you got that. It's this two-panel view.
It's the wrong screen. Oops, sorry, I should not.
And I am going to switch over the browser, so is that going to cause problems? Okay, so thank you. And I think I have the opportunity to finish the session today on something totally different, as we've heard and seen a number of use cases for Pangeo that focus much more on the high performance computation, the data intensive computation, a lot of the capabilities that Pangeo brings for actually doing science. The use case that I'm presenting today is very different, and it's based on the workshop platform and content that we've been developing at the University of New Mexico over the past 2 years, actually developing training materials for novice users and novice users of analysis tools. And the initial approach that we've taken in developing and managing that content and using tools for making that content usable and actionable in the workshops, and how we are looking at Pangeo and similar platforms for being able to more efficiently and more easily, from a perspective of both the learners and the instructors, be able to leverage the content and make our workshops more interactive and continue this focus on interaction. So the workshop series that we've been developing over the last few years has grown to about 15 different modules, many of them developed in a Jupyter Notebook environment. We've actually, even for topics that are not Python centric, we have used the Jupyter Notebook environment even as sort of using the Markdown capabilities to develop presentation and reference materials for the workshops. We've also leveraged the terminal environment that is available in a Jupyter Notebook platform for being able to do command line based tutorials. So we've been able to leverage the capabilities of the Jupyter environment for a wide variety of workshop topics. And that has allowed us to have an operational platform for being able to not just present concepts, but have an environment when appropriate where we can we can actually execute, and our learners can execute the code and the concepts that we're teaching in the workshops. We've been doubling down on that as we're now adopting more of the Carpentry's live coding approach. So we even have a stronger emphasis on interactive coding throughout our workshops. And this is just a list of some of the topics that we're focusing in. And in terms of our Jupyter Notebooks and our start, and it really is a start in experimenting with Pangeo and related platforms for being able to support our workshops, we're focusing on the Jupyter and command line workshops. But eventually we'll be looking at ways to try to streamline our R-based workshops as well. That have to date been based on web-based RStudio. And looking whether it's an RStudio server approach or transitioning some of that content into R-based notebooks. We aren't quite there yet, but that's essentially where we're headed. So at the very beginning, we had already adopted a workflow for developing our workshops that was based in GitHub. So we were already very comfortable working in a combination of Markdown and code. So it was a very natural approach for us to do our development in Jupyter Notebooks, and then also work in RStudio in our projects. But as I said, all of it was already being maintained in GitHub. The GitHub repository that our team has developed, where we manage all of this content, is down here. And I welcome you to go ahead and check out what we've done and provide any feedback or reuse, repurpose, provide pull requests, whatever you'd like to do. But this is the core of how we started to develop our process. And initially, we were just essentially managing the content and presenting the workshops from those individual repositories for each workshop. Very quickly, we decided that it would be more efficient for us to actually have a corresponding teaching and learning platform that we could use to provide a unified environment, both for us as instructors and an environment for the learners that was customized to some extent with the particular tools and configurations that we were using for a particular workshop. This is where we ended up developing a Docker container-based environment and platform, and this is also in that same GitHub repository, where it's a set of orchestrated containers that we can spin up and provide the Jupyter Notebook environment, the associated command line tools that are installed in the system, or also the hosted RStudio platform. And what this gave us was the ability to run a local instance of this teaching and learning environment on our teaching workstations. Our students could actually, if they had Docker installed on their system, actually run the entire environment on their system, including the content of all of our workshops. So they would have all of the content through literally a Docker one-line command that would spin up the entire environment and its content on their system. And it gives us a nice independence and separation between the content of the individual workshops that are managed in separate GitHub repositories and a platform that can be used for actually interacting with that content, being able to execute the workshop materials as we would go through them in a process. In doing that, we have learned some lessons. While it has proved to be incredibly efficient and helpful for us as teachers, as instructors, having this ability to be able to iterate quickly and maintain our content and version control, and having this platform that we can run on, whether it's in the cloud, in Amazon's cloud, whether we're running it on our local machines, and multiple local machines, and we can use essentially GitHub and the repositories as the authoritative source for the current versions of all of our content, our learners weren't really interested, especially in the process of installing and running Docker on their system and then running again. I say, oh, it's just a one-line command. Well, that one-liner plus installing and running Docker proved to be a significant barrier to our learners, where they were coming to a workshop to learn programming basics or command line skills or natural language processing with Python. So we actually did not have significant uptake from our learners when it came to adoption of this teaching and learning platform in the environment we had created. So this is what has, but we did learn that there was an appeal of a web-based platform as a backup for locally installed applications by the learners. When they came to the workshops and they did not have a Jupyter Notebook environment on their system or an RStudio environment on their system, the fact that we had an instance of this environment running, in this case in Amazon's cloud, that we could point them to, that was a very helpful and useful backup for our learners so that they wouldn't even necessarily have to have installed anything on their system other than just having an internet connection in a browser. So that web accessibility remained an issue. Is just they didn't want to necessarily jump through the Docker hoop to be able to run a local instance of the content. So this is where we've adopted what I've been characterizing as our unplanned plan B, because we have unintentionally benefited from our early decision to maintain our content in GitHub as just a standard practice, as separate repositories for each of our workshops, adopting Jupyter Notebooks as a common platform for both the sort of the narrative and presentation materials, but also, when appropriate, the executable code and examples associated with the workshops. That positioned us really well to be able to have a lot of options, as those options have emerged for connectivity into GitHub repositories, just like Pangeo or Binder provide, for being able to have interactive notebook sessions. So as a result, where we are heading now, and we've actually done one workshop based on this so far, and it did not go down in flames, so we're optimistic that we can continue doing this, is we're working with our High Performance Computing Center at UNM to actually set up a local Jupyter Hub environment, and I'm going to start working with them on a Pangeo environment as well, but also initial experimentation with Pangeo as a deployment environment so that we can share that simple Pangeo link for a pre-built workshop module in that environment, so that our learners can very quickly follow that link to be able to go through our training sessions without having to do any installation on their system, and in this case, without us having to maintain a separate learning environment in the cloud resources using our previously developed platform. We're still finding the instruction platform for ourselves very useful, but this gives us a tremendous amount of flexibility in terms of how we can leverage our existing investments in the content in GitHub and being able to have a lot of different deployment options. So I was going to spend my remaining time just providing a very quick illustration of sort of the use case we started with, and as we're transitioning it into a Pangeo-based scenario. And I'm actually going to start out with a link that is not on the screen here because I realized after the fact that I had not included it. So if I open up my browser and I go to cc.unmrds.net:8888. This is our learning. This is our learning environment. Yeah, I thought you might have to do that. This is our learning environment. It's hosted in Amazon's cloud. When we designed the system and built our container process, we have options for establishing essentially two environments. One for the instructors to be within, one for the learners to be within. So we were able to try to anticipate a scenario in which our learners could somehow break things, or we could break something, and we wouldn't necessarily impact the other users. That is also an artifact of the fact that at this point, this is a system that is based on what is still essentially a single user optimized notebook platform. It's not a Jupyter Hub sort of scenario. So that's a more significant concern in that situation. So in this case,
it's annoying. 1 second.
There we go. I can take it from there. And the password, if you're following along from home, is just C and C, the number 2, GO. Maybe. That's if I can type. The C and the ampersand C, the number 2, GO, code and coffee to go. And this is the totally unintelligible notebook environment. And one of the things I'd point out here is that we built this system so that when you restart the containers, one of the first things it does as a part of the initialization process and the orchestration of the containers,
It's still not showing online, so sorry,
is that there's a script that we maintain in version control that actually provides a list of all of the workshop repositories that we want to have automatically synchronized into the environment. So every time you restart the containers, you're going to get a current set of all of our workshops. We also have that script inside the environment so that if you have a long-running process as we do in our learning system, you can actually run this refresh workshops.shell command, and that will pull in with just a git pull command the current state of all of our workshops, so that it's very easy for us as we're going through. I'm sure nobody else does this. The night before a workshop, the final revisions in the morning that you're getting ready to actually present it, needing to pull the updates. So this is a capability that we built into the system from the beginning, and then each workshop has its own folder, and we then basically have a set of notebooks and associated materials in each of those folders that represents the repository that workshop is based on. We also then have, and I won't go into the GitHub, but I will just describe, the content platform itself is basically a collection of Docker Compose configuration files that you can use in a Docker environment to build the combination of containers that are appropriate for a particular use case or workshop. So if a learner wants to just have a functional environment from themselves, they don't need to spin up the instruction container. If we're doing one of our NoSQL sessions, we have an alternative one that will spin up the NoSQL containers. So we have some options, and that's all a part of this content platform repository. Our programming concepts with Python repository is just that. It's the content associated with that. And the one thing I did want to show is that in Pangeo, as I pushed this updated version in last night, hopefully it will show up. We're able to, in Pangeo, bring in the current snapshot of this particular workshop's content for each learner to be able to have the interactive access to both the instructional materials and the sample code and the actionable sort of walkthrough that we're using in our live coding approach to these workshops. So it has turned out to be a very easy and streamlined approach for us to be able to essentially replace our more intensively managed instruction platform with a much more interoperable and broadly usable technology based on Binder, and in this case, Pangeo, where we're not even scratching the surface of Pangeo's computational capabilities, but it does give us a lot of options for being able to do more computationally and data intensive instruction sessions, since we now have the opportunity to have access to some additional computational horsepower behind the system that we never, to be honest, were prepared to pay for in our EC2 instance that we were using to host the environment. Oh, I see. It didn't change that screen. So I have to, this is the joy of presentation mode. Now, so if I escape from here, and then, there we go. And so as I said, this is sort of a standard Jupyter environment, but we have basically been able to provide access to all of the content that we had previously used in our other environment based on the exact same GitHub repositories, and essentially independent of what platform we're using for the instruction. The students have access to the exact same content and can interact with it to their heart's content. So with that, I'm finished and happy to take any questions.
Very much, Carl. So we have about 3 minutes left, and then we'll be plenty of time. Any questions for Carl?
It's really just a comment that we also have been using Jupyter, or the Pangeo environment for training, and it's worked really well. I don't know if you mentioned this, but obviously the Kubernetes scaling that works for doing these big computations also works for lots of students.
Right. And that was, to be honest, that was the pleasant surprise that I experienced in the first workshop we used this for, where we had done limited testing ourselves in terms of trying to open up multiple instances and seeing if we ran into any issues, and it did scale nicely in our testing. And in a larger group of close to 30 learners, I did not hear any complaints from folks not being able to access the content and be able to follow along.
Any other questions for Carl?
If there's no other, just one thing to also I forgot to mention is that people ask how much does this stuff cost, and how much did it cost to do your to run your, well, you were using Pangeo, so you're not really sure what the costs were, I guess, but. Well,
I certainly know what the costs are for our EC2 instance, which, is running, about $60 a month and then it's configured to be able to scale somewhat, but Amazon has an interesting model for being able to scale parts of instances, but typically not all the parts you need. So that has been one of the really useful parts. But yeah, we haven't done the deployment locally to see in terms of overhead or other associated costs to stand up our own instance.
Yeah, just one further, just last thing on that cost issue. I know a lot of people come up and ask me afterward, like, how much did that demo cost with all those, cores running and everything, and it's like 7 instances that they're running on spot that cost 10 cents an hour. So like so if we ran that thing for an hour, it'd be 50 cents. But since we ran it for 30 seconds, it's like less than a penny. So.
Right.
All right, let's thank our speaker.
Great, thank you.
Oh, we have one.
How are you measuring the success of this activity?
In terms of the learner response and learning process?
Yeah.
That's actually been a moving target for us, and we have some initial assessment tools that we've developed, but to be honest, we are still working on getting those deployed to our learners. And as a matter of fact, there's a session this afternoon related to work that I and Nancy Hobel-Heinrich are doing for the Data Management Training Clearinghouse, where we have a specific focus on developing assessment capability that can be applied to any of the training materials that are in the Data Management Training Clearinghouse. And to be honest, I've been sort of distracted with that broader focus, and we haven't, it's sort of like the cobbler and the children's shoes. We haven't quite brought that home yet.
All right, thank you all for attending this session. I hope it was useful.